Hello everyone. Today I am going to present the work Optimal Placement and Power Supply of Distributed Generation to Minimize Power Losses. This work is done by me, Shijie Pan, from King Abdullah University of Science and Technology, together with Sajid from University of Warwick, Professor Subhash from University of Warwick, and Professor Constantino from King Abdullah University of Science and Technology. As the title suggests, we tried to design an optimization strategy in our work to minimize the power losses. So why is reducing power losses so important? Let me first show you a table. This is the table of supply and disposition of electricity in New York from 2019 to 2021, and is published by US Energy Information Administration. As we can see, the total supply annually is around 150 million megawatt-hour, while the estimated losses reaches around 7 million megawatt-hour. That means 5% of the total power supply is lost. And considering the electricity price in New York is about 20 cents per kilowatt-hour, more than $1 billion is caused annually by the power losses only in New York. So our question is, how could we reduce power losses and to further reduce the bill we need to pay? Let me first give you a toy case as an example. Assuming we have 7 houses that require the same electricity power and they are connected by electrical lines as shown in the graph. Also, we have a DG, which is a PV panel in our case, that provides the power to the grid and is located here. How will the power flow from the PV to the users? As we know that the power always flows from the supply side to the demand side. It will flow like this. We can notice that for these 5 houses, the power has to go through 2 paths before they reach the end users. But what if we put our PV here in the center of the grid? Now the power will flow like this. And for these 5 houses, the length of the path is reduced from 2 to 1. And for these 2, they just switch their path. And considering the impedance on the electrical lines, which means shorter paths, less power losses, we can say that in this scenario, placing the PV here in the middle is a better solution than putting it here. And it tells us placement of DGs matters. However, in practical, we have much more houses with different load demand. We have different impedance on each line, and we may have multiple DGs in the grid. So our first research question is, if we plan to put multiple DGs in the distribution network, how should we place them and what should be their size? Well, the answer we give is to use a mixed integer programming. We choose a binary variable a, which is either 0 or 1, to denote whether there exists a DG at location I. With this variable, we can write down 2 constraints. The first one bounds the upper limit of DG apparent power capacity. As we have the a here, we can make the right-hand side term to be 0 when there is no DG, and the active and reactive power supply will be also 0. For the second equation, it represents the total number of DGs in the distribution network. With the constraints we formulated, we can look for the optimal locations to place DGs in our system. Also, if we make the active power supply, which is PI supply here, to be an optimization variable, we can also get the corresponding optimal size of DGs. Then our next research question is, after we have the optimal placement of DGs, how should we operate them in proper ways to reduce the power flow losses further, and considering various load demands in the system? If we think about nowadays, we have inverter-based energy resources that can provide controllable reactive power. We can use the reactive power compensation, which is to make the DGs provide the optimal reactive power output to further reduce the power flow losses in the system. For other considerations, we have this flow model, conservation voltage reduction, CVR, and the IP load model and voltage and current limit. Let me talk about them more in detail. The disk flow model is a branch flow model used to calculate the power flow in the system. It is designed for radio network, which is also a property of the distribution network. We have the active power and reactive power equations. We have nodal voltage balance, and also the apparent power calculation, of course, with the relaxation. The V square and I square in the model are substituted by V and L to make the equation linear and to simplify the optimization. For CVR, which is conservation voltage reduction, it varies bus voltage in around 5% range without causing damage to the equipment. And because of this varying voltage, we want to build a relationship between load voltage and load power demand. So we introduce the VIP load model. Also, it needs to be linearized before applying into the optimization formulation. And here is the VP load model after the linearization. And to give a more visual illustration of how our optimization strategy works, here is the structure of our two-stage optimization. First, we look for the optimal placement of DGs in the system, and then we run the second stage optimization continuously to find how much reactive power the DGs should supply according to different load demands. And the right part here is the mathematical formulation of our optimization. We have the starting part considering the placement. We have the disk flow model. We have voltage and current limit, and also the power flow equations considering the VP load model. To test our optimization strategy, we code the problem with convex pi and solve it using Cplex solver. We further built the IEEE 15-bus system and the IEEE 33-bus system in the Dick Silent Power Factory to verify our optimization results. In both systems, we consider CVR and the IP load model for the loads. We gradually increase the number of DGs in the system and test their behaviors in the different stages of our optimization. Let's first look at the power flow losses before and after different stages of our optimization. Noting that in the basic IEEE 33 or IEEE 15-bus system, there is no DGs in the grid. So we can say the result with NDG equal to 0 is the result of the original power losses in the system, where we have around 58 kilowatts in the IEEE 15-bus system and around 180 kilowatts in the IEEE 33-bus system. After we apply the stage 1 optimization, which is with the optimal placement and sizings of DGs. As the blue lines show, we can have the power losses to be significantly reduced from 160 to around 30, which is by half in the IEEE 15-bus system, and from 180 to around 60 kilowatt, which is to the 1/3 of the original one in the attribute 33 bus system. And after the stage 2, reactive power output optimization, we can make the power losses even much less, to be around like 3 kilowatt in the attribute 15 bus system and 5 kilowatt in the attribute 33 system. What's more, if we look at the voltage profiles of the systems, we can see that before the optimization, which is the purple lines show, the voltage are low and even violate the limit, which is 0.95 per unit. This is even more serious in the attribute 33 bus system. But after the optimization, the voltage are put up and can be well maintained at 1 per unit, which is quite good. Furthermore, we want to test if our optimized system can work with enough robustness, so we manually increased a load by 50% at a time to see how the power flow losses will be changed due to the load change. The blue line shows the results before the optimization, and the purple lines are the results after. As we can see, the variation in the power losses is sharply reduced. Before optimization, we have the biggest variation in power losses to be around 7.6 kilowatt at bus 8 in the attribute 15 bus system, but it is then reduced to 0.71 kilowatt after the optimization. And also we have from 36 kilowatt reduced to 2 kilowatt in the attribute 33 bus system. Also, we want to know the change in the voltage profiles, so we check the voltage profiles of the system when there is a load increase at bus 8 in attribute 15 bus system, and it loads at bus 31 in the attribute 33 bus system, which are where we have the biggest power loss difference here. We can also see that even though there is still some variation in the voltage, because of our optimization has pulled up the voltage to be around 1 per unit, we can have much more margins before it drops and violates the limits. And this tells us the optimization makes the system more healthy. So as a conclusion, we proposed a two-stage optimization for minimizing power losses in distribution grid in our work. With the optimization, the power losses can be significantly reduced. And voltage profiles of the system can be well maintained to be around 1 per unit. Also, the optimized system can support additional load due to power savings. But there are still some limitations in our work. To extend our work more in the future, we can incorporate device modeling from on-load time changers, capacity banks, and energy storage systems into optimization. We may also consider daily or historical data of load profiles and power generation to do day-ahead scheduling of the system. And we want to model the uncertainties and imbalance in distribution system by using stochastic optimization or reinforcement learning, and by model the system in 3 phases. That is all my presentation. Thank you for your attention.